Okay, so let's start where we left in the previous lecture, where if you recall, we defined kernelization and gave a kernel for point line cover, vertex cover, and we also gave kernel for edge click cover. This were like order k squared points, order k squared vertices and edges, and this was like 2 power k vertices, and so since there are only n square edges, so it will have at most 4 power k edges, right. So, notice that these first two kernels has polynomial bound, but the last kernel is exponential, and so a natural question arises is that is there a polynomial kernel for this problem? If not, can we prove that no such kernel exists? Okay. Okay. So, we will see such methods later in the course to show that kernels of certain kind do not exist, but for now we will continue our foray into discovering techniques to design polynomial time kernels. Okay. So, there is a very well known notion about is FPT same as kernelization, okay? And let us see if we can say any statement like this. So, for a parameterized problem Q, we can have one of the following things. Q admits a polynomial kernel, right? This could be one statement. Q admits a kernel may be exponential, like this is like vertex cover or point line cover, admits a kernel like exponential like edge click cover, or Q admits no kernel, right. Now, notice, so it is very natural, right, to say that the moment Q admits a kernel, Q is fixed parameter tractable, right, because look at why we say this. Suppose look at a vertex covered example, right. So, what did you do given, or say point line covered example, right. So, in point line cover, given a set of points p k, in polynomial time we got an equivalent instance p prime k prime, where in fact k prime was less than equal to k and p prime was less than equal to k square, right. Now, to check whether there exists k lines that covers all the points, we know that how many number of lines that we need to consider. The total number of lines that we need to consider are like at most k power 4 lines, and from this k power 4 lines we need to choose k power 4, choose k lines and check whether they cover all the edges, all the points or not. So, how many such possibilities are there? So, k power 4 choose k is like roughly k to the power 4 k, right, which is like 2 to the power big O of k log k times n to the power big O of 1 to n to the power big O of 1 to get the kernel and to check all these things. So, we do get a kernel, right. So, once we have a kernel, it seems that an obvious way of trying these answers is good, because size of the instance itself is bounded by some f of k, right. So, it seems very obvious that if Q admits a kernel implies Q is FPT, but this may not be true all the time, because this is something which if you do not understand, it is perfectly fine. You can, size is some function of parameter, okay. That does not imply the problem is FPT. Why? Because I may not have an algorithm, right, to even make a decide whether this is a yes instance. So, basically what we need at this point of time is our problem to be decidable. Okay. So, we say this is a statement from world of computability, that a language problem, whatever you want to call it, L is decidable if there exists a Turing machine Turing machine M such that language accepted by Turing machine is exactly equal to L, and M halts on every input, okay, which implies that, look, a language or problem is decidable if there is a Turing machine, like on every input it will tell you yes or no, right? If we have such an algorithm, then basically Q admits a kernel implies Q is FPT. It basically says, well, if Q admits a kernel and there is some algorithm for Q, then Q is FPT. Okay? So, this is an important point to talk about, and every kernel or every problem that we will consider in this course, and in particular every NP-complete problem has such an algorithm. So, if you are dealing with NP-complete problem, don't worry at all, they are decidable by definition. Okay? But there are problems which are not decidable, and okay, so I will not go into any detail here, but if you have any, if you like to know example that problem admits a kernel but no algorithm, but not FPT, ask me by sending an email or some such thing. Let's not confuse the readers with this, but all I want to tell you that do remember that if a problem admits a kernel and it does has an algorithm, then it does imply the problem is FPT, because it just all that it means that, you know, size is any bounded, you now run the algorithm to make a decision about it. Okay. 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 But what about the other bit? So, Q is FPT implies Q admits a kernel. What about this? So, this is nice that even the reverse, if Q is FPT, then actually Q admits a kernel. Why? So, suppose Q is FPT implies you can decide whether I comma k belongs to Q in time some f of k I like instant to the power say by some algorithm A. But remember, this is why FPT is computable. This f by definition is a computable function. F is a computable function. Means there is a Turing machine which can, given k, you can write f of k. So, what does the kernelization algorithm does? It runs this algorithm A for mod I to the power c plus 1 steps. Okay. So, either this algorithm just ends by then and tells me the answer. So, I have run the algorithm for mod I to the power c plus 1 steps. If it does not terminate, then I will say, hey, I comma k is your kernel. So, it is a very trivial algorithm. It is a very trivial algorithm in the following sense. What I do, I run my, so suppose the instance size I is equal to n. So, I run this algorithm for n to the power c plus 1 steps. If it terminates, then we are happy because we have found the solution. I return you that as a solution. Or if it does not terminate, it runs beyond this, then I return the instance itself. And this is for this termination point that we needed to know whether f is computable or not. Okay? But beside that point, so what happens? It means if it ran for more than this step, it means, let us see what happens. It means f of k mod I to the power c is greater than or equal to mod I c plus 1, which implies that mod I is less than f of k. So, you have indeed got a kernel, right? But how interesting is that a kernel is a different thing. So, which implies that this is why in this, if you talk about decidable problem, then the notion of FPT and kernelization are same. So, we could have defined FPT in terms of kernelization also for decidable problem. Okay? So, but the kernel which comes from this theorem is basically the function of the parameterized algorithm, and that is not what it is all about. So, it is all about that how smaller kernel can we get if we just allow ourselves to be polynomial time. For example, for vertex cover, if we want to solve an FPT algorithm, if you want to design an FPT algorithm, we cannot do better than c power k modulo some conjectures. But we are able to get a kernel with order k square vertices and edges. So, in polynomial time, we can do much more than just getting a kernel with exponential size. Okay? So, the field is interesting also because that our main goal is to determine which problem admits polynomial time kernel, which problem does not admit polynomial time kernels, and can we show these things, how small kernel we can get, and things of this nature. Okay, let's moving ahead. Let me give you another example of kernel problem. Okay, so my input is an universe U, okay, D heating set, a family S of size at most D over a universe integer k, and our question is, does there exist a subset X of U of size k that has a non-empty intersection with every member of S? So basically you are looking for a set, a subset X of U whose size is k and it intersects every set. So this is a very classical heating set problem, and it is D heating set because every set in the family is upper bounded by D. So for example, this could be your set family, right? Yellow, blue, white, green, right? And they are intersecting things amongst themselves. Okay. So we would like to make a kernel for D heating set, but I will but I will instantiate. So we would like to get a kernel for D heating set. So before we go to D heating set, let's observe that 2 heating set is nothing but a vertex cover. If every set has size 2, then this is a vertex cover. And what was the kernel for a vertex cover? If you recall, there were just 2 reduction rules. Isolated vertices were useless for vertex cover, right? Isolated vertex were useless for vertex cover, so we deleted them. Let's see if I can use, okay. And if a vertex is incident with k plus 1 edges, if you recall correctly, if the vertex was incident to some k plus 1 edges, we included V in the vertex covered and decreased the parameter by 1, because every vertex of this should be in the solution. Now what we try to do is like try to mimic this kernel for vertex covered for 3 heating sets. So now let's assume that D is upper bounded by 3. Okay. So what is this? If an element V is not contained in any of the sets, then there is always solution without it, right? It is same like isolated vertices. What was that? If a vertex V okay, so we are making some observation, right? So what is our observation? Let's try to add a page, maybe that will be helpful. Okay, so what is, if an element V is not contained in any set? So an element is present in the universe, okay, is present in the universe, okay, but this element doesn't occur in any set. So it is same as saying that a vertex is not part of any edge. So it's an isolated vertex. Then we can delete V without changing the answer. Now notice, if an element V is contained in k plus 1 sets S1 to Sk, so basically suppose you have a sets, here's V, and these sets do not intersect but at V. So if you look at this part, look at this, they are disjoint, so on and so forth. Okay, so these are like disjoint. So this is what it means. If an element V is contained in k plus 1 sets S1 to Sk plus 1, so they are like V is present in S1 to Sk plus 1 sets, okay, and Si intersection Sj is exactly equal to V for R. So if you look at any set Si and Sj, their intersection is exactly V. So if you look at any pairwise sets, they only intersect at V. So now what happens if you don't pick, in fact, if you don't pick V in the solution, then notice there are like k plus 1, then there are like k plus 1 pairwise disjoint sets. Who will hit them? Because to hit this k plus 1 pairwise disjoint set, you at least need k plus 1 points from U, right? So in that implies that V must be included in the solution, right? So this is same as a vertex covered analogue. If there is a vertex of high degree of degree k plus 1, then V must belong to the solution. This is same as saying if V is part of k plus 1 sets, where V is the only set which is common to all this, then like for you take any 2 pairwise set, V is the only common element between them, basically they look like the picture which I have drawn, then V must belong to my solution. Okay. Now what can you say that, look, I cannot say about V, but I can actually find two elements, UV, and now I have an extension of this k plus 1 sets, okay, here. So, if I delete UV, then all these sets are pairwise disjoint. Then what happens, right? Then what happens? If you do not pick one of U and V, then you again need k plus 1 elements to cover all these sets. So, it implies that for all I not equal j, then at least one of UV should be in the solution. Okay. So, now let us formalize this intuition into the reduction rule, and it is done as follows. So, what are my reduction rule? If an element V is not contained in any of the sets, so reduction rule applies delete V. If an element V is contained in k plus 1 sets S1 to Sk plus 1 such that Si intersection Sj is V for all I not equal to G, then what is our reduction rule? Right? Make a new set V, delete all sets S1 to Sk plus 1. Why? Because look at the forward direction. You know that V goes into the solution, then V and every other one else, okay, I will formally prove it, okay, in a minute, or you can prove it yourself for this, will contain this. And in the backward direction, because you have kept the set, single set V, like single element set V, the reduced instance must pick V. The moment you pick V, S1 to Sk plus 1 will be hit in the original instance, okay. And if two elements UV are contained in the sets k plus 1 sets such that this, then, okay, then what you did? So, look at this, what happened. So, you have U, family and K. What you did here? You in this you did a U, and F prime is F minus S1, S2, Sk plus 1, and but you added set U. Okay, leave it. Okay, plus UV. Okay, and this is what we did. So, this is I returned F prime comma K. Now, let us see what happens. So, forward direction, right, look at the forward direction. Well, in the forward direction you know that if there exists a set X subset of U that intersects all sets in F and mod X is less than or equal to key, implies X must contain U and V. Then I claim that X also intersects every set in F prime. Why? Because look, F prime has all the sets like which F contains except UV, right, and X is the same, then you have taken care. And now, since X contains U or one of the V contains one of U comma V, X also intersects every set in F. Reverse direction is also obvious. X intersects every set in F prime implies X contains either U or V, implies X intersects all of F. Because why? Because look here, what was the difference between F prime and F? Well, F prime contains all the sets of F but S1 to Sk plus 1 and it contains UV. Now, because F prime contains UV, you know that one of U and V must be taken in my X, but then that U takes care of S1 to Sk plus 1 or that V will take care of S1 to Sk plus 1 and the remaining element of X will take care of other sets of F. So, this is it. So, this is a very simple reduction rule and we can prove its correctness immediately. Okay. So, but how many sets are in an irreducible S instance? Because how are we obtaining a kernel? We are obtaining a kernel by the following procedure. We apply some reduction rule and we say when reduction rules are no longer applicable And if this is a yes instance, then the number of sets, number of objects are bounded, because if they are not bounded, then I can say no, and then we are correct. So, let us try to do the same analysis for the problem. Okay. So, to do the analysis, I am going to do the following. I have u, comma f, comma k. Okay. Greedily compute a maximal family of pairwise element disjoint sets from F. Okay. So, we have greedily compute. So, suppose this is like S1, S2 dot 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 Sn. First of all, if L is greater than or equal to k plus 1, say no, right, because now I have k plus 1 element disjoint sets and you want to hit all the sets with just k elements, then for this k plus 1 sets itself you need k plus 1 elements. So, you sense. So, we can assume that L is at most k. So, now if I take, say, let us not call it x, let us call it z, which is union of xi, I going from 1 to L, right, then size of z is at most 3 times k. Okay. Now, observation 1, okay, and suppose this is an yes instance. Okay. So, if it is yes instance, L is always be less than or equal to k. Okay. Okay. Now, look at observation 1. What is this? For every element u comma v, number of distinct sets that contain u v is upper bounded by k, otherwise we would have applied the reduction rule C, right. This is else reduction rule C is applicable. I am going to claim for first of all, what is observation 2? Z is a hitting set for F. Why? Because a maximal element disjoint sets from F. So, if you cannot add any sets, why? Because this set intersects one of the sets previously selected set. Okay. This is, so Z is a hitting set of F of size at most 3k. Okay. 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 Now, this is our main claim. Every element in Z intersects at most some, we will fix some k square, some question number mark k sets. So, basically some order k squared sets. Okay. Let us see why. Okay. Because once we are done, then we will be happy. So, why? Let us fix a element w, this is in Z, and suppose it participates into lots of sets. Okay. Okay. So, suppose it participates into more than some k square plus some sets. Okay. We will see what happens. Okay. So, what is a common about these things? W is inside each of this set. Okay. Now, let us pick up the first set here. Okay. I pick up an element here Z. I pick up an element here Z, and I ask myself, among these sets, among the sets, among these sets, how many of them contain Z? How many of them contain Z? Let us ask ourselves, suppose Z was here, Z was here, Z was here and Z was here. So, let us pick up, so first of all we picked up W, now we picked up Z and we picked up all the sets which Z contains. Well, this can be at most k of them, right? Otherwise, Wz is common with k plus 1, Wz is common in k plus 1 sets, which implies reduction rule C is applicable. Okay, that's correct. Now, so Z appears. Okay, now let's ask ourselves, how many sets? Suppose how many sets? Suppose there is another element y, right? How many sets contains y? Same way we can say, hey, look at Wy and look at all the sets it contains. It is also at most k of them. Okay, great. So now what I am going to do, I am going to pick up Zy, I am going to pick up this set and delete all the sets. Okay, okay. So what I do, I pick up the set W, Z, Y, and now delete all sets that contain either Z or Y. How many sets will we delete such? By this process, we will delete at most 2k sets. Okay. So, but now we have got a set W, Z, Y. In the remaining set, do the same. What will we get? Right? What will we get? So, if this process continues for k plus 1 steps, what do we get? We get W, Z, Y, some other set, some other set, some other set, some other set. We get k plus 1 sets that are pairwise intersecting only at W, but then reduction rule 1 or B is applicable, right? W, you should have a set containing just W, which implies that this process can only continue for k steps, right? Which implies that in each step you knock out 2k sets. In each steps you can, so basically you will get, if you get like, you cannot have more than 2k square, because in each step you knock out 2k. So, you cannot have more than 2k square set that contains an element of Z. Okay. So, let us go back. So, 2k square is the right language. We did not know what it is, but now we have got it. 2 is k square, we can fill it. Okay. Sets. At most 2k square. Okay. Now, what do we know about Z? Z is a hitting set, right? And so, like Z1, Z2, Z, say at most 3k, each element occurs in at most 2k square sets. So, the total number of sets are 2k square plus into 3k plus the sets from Z1 to Z3k, which was like at most k. So, which is like into 3k. So, this is like 6k square plus k. So, total number of sets are at most 6k square 6k cube, right? There is k cube here. Number of sets is at most 6k cube plus some roughly k. So, the number of elements will be like you multiply with some 3 here. So, that will be like order k cube number of elements, right. So, this is how you can get a kernel for 3 heating set, just generalizing the idea of vertex cover. And in fact, this follows from, which I did not teach you, the notion of sunflower. So, what is a sunflower? So, you have sets S1 to Sk form a sunflower. If the sets Si minus Sy look at, so they just have a one common intersection, otherwise they are pairwise disjoint. Okay. So, right. So, Si minus their common intersection are disjoint. So, this is called center, and actually these things, if you delete the center or delete the common intersection, whatever these are called petals. So, in as early as 1960, Erdos and Rado proved the following lemma: if the size of system is greater than p minus 1 to the power d times d factorial, and it only contains set of size at most d, then the system contains a sunflower with p petals. So, in our case, we applied this with p equal to k plus 1. So, if you have more than k power d factorial sets, then you will contain a sunflower with k plus 1 petals, right. And furthermore, in this case, you can find such a sunflower in polynomial time. So, how do we get a d? If k plus 1 sets forms a sunflower, then remove these sets from S and add the center C to S. S does not hit one of the petals, thus it has to hit the center. Note, if the center is empty, the sets are disjoint, then there is no solution. So, if the rule cannot be applied, then we know that number of sets is upper bounded by k power d, and you can get a kernel for d heating set applying this classical sunflower. And the proof is of this lemma is not very hard, and you can find in the textbook of the course. Okay. So, d heating set admits a kernel with k power d sets. Okay. So, before I end my lecture today, let me give you another problem which is very classical and which has, okay, it's called d set packing. Okay. So, Unipet is universe, a family S of sets of size at most d over u and integer k, and the question is, does there exist a subset X of S of size k so that all sets of X are pairwise disjoint. Okay. So, here for example, A, B, C and E, F, J are pairwise disjoint. Similarly, C, G, H and B, D, E are pairwise disjoint, and there are only 2 pairwise disjoint sets. So, in the D set packing, our goal is that can I find k sets that are pairwise disjoint? So, I will just give you a let us look at 2 set packing. So, 2 set packing is nothing but you want to find 2 sets which are pairwise disjoint, and basically if you think of 2 sets, then they are like a graph, right. Each you think of universe as vertex set, think of universe as vertex set and universe, and for each 2 side edge you just put an edge, right. So, this is basically a graph, and 2 set packing is nothing but finding a maximum matching in a graph, which you can do in polynomial time. But forget for now. Notice that if I have a vertex V whose degree is say 2k plus 2, okay, then I claim to you that you can forget one edges, you can delete one edges incident to V, and now we can show that G has k vertex k matching if and only if G prime has k matching. So, look at the forward direction. Backward direction is very easy. Okay. So, the backward direction is very easy. Why? Because backward direction is very easy because here's a G prime. Okay. So, any matching in G prime is a matching in G. So, if you give me a k-sized matching in G prime, I can get k-sized matching in G. But what about the forward direction? That's a interesting point, right? So, the point is, look at forward direction. We had 2k plus 2 edges, right? And what happens is that in G prime, some edge is missing, this edge is not there. So, you let us look at a matching M of size k in G. Let us suppose this is edge u v, this is edge u v here. Two things: contains u v, does not contain u v. This is easy. Does not contain u v means then M is a matching, fine. But now it contains u v. Okay. If it contains u v, then what happens? If M contains u v, look at this u v. Let us delete this u v. Now, because you delete u v, what happens? Now, I need to find, because it contained edge u v, it contained an edge because it contained an edge u v, you know that no other edge incident to v is selected in M, fine. Okay. Now, let us look at this u1 v1. Okay. Maybe this edge and this edge I can't, this edge and this edge I can't, I would like to, what I do? I would like to replace in the M u v edge by some other edge which is present in G prime. That is my goal. Okay? That is my goal. But unfortunately, this edge is okay. So, let us look at this u1 v1. Just one second. Okay. So, that is our objective is to replace u v with some other edge, okay, objective, replace u v with another edge incident to u in M that is present in G prime. Okay. So, let us ask ourselves, what about this edge? Oh, I cannot pick this edge because there is some vertex, some edge which is incident to this vertex, fine. So, an edge can only kill two edges, some other present edges can only kill two edges incident to u. So, by doing this, okay, this cannot be done, this cannot be done, this cannot be, but how many? Number of edges that we can't select or those edges that intersect with vertices in V of M minus u v is at most 2 times k minus 1. But what was the degree of V? Degree of V is greater than or equal to 2k plus 2. So, after I deleted one edge, degree of V became degree of V is at least 2k minus 1. Now, I deleted 2 into k minus 1. So, degree of V is at least say let us say 2k minus 1 minus 2k. No, it was 2k plus 2. I deleted this. So, let us see how many edges are. Okay. So, maybe we need at least 2k plus 2. So, say this is my bad. So, say degree of V is at least 2k plus 2 plus 1. Okay. So, even after I deleted, so maybe we should do oh, that's my bad. Okay, this is something. Okay, so we started with 2k plus 2 edges. One edge we are not allowed to pick because of UV. Okay, and these many edges are deducted because of this. So, let us see 2k plus 2 minus 2k minus plus 2 minus 1, which is so 3. So, we still have lot many more edges left at V that we could replace that edge of M with this particular edge and we can get. Okay. So, basically what it tells us that if you are looking for to preserve matching of size k, and if a vertex has very high degree like 2k order k plus order k like 2k plus 2, then you can do something interesting, right? You can delete an edge. We can apply the same kind of idea, but using so you can prove that if a set contains a sunflower with dk plus 2 petals, one set of the sunflower can be deleted. So, you can apply this reduction rule based on sunflower and get that D set packing admits a kernel with order k to the power d sets. Okay. Okay. So, that is the last kernel that I want to touch. So, there are more problems one can kernelize like cluster editing or feedback arc set in tournaments. Look at the exercises that will come follow. So, let us just summing up these 2 lectures on kernel. So, we saw some simple kernel for vertex cover, point line cover, edge click cover. We saw when FPT is equal to kernelization, under what condition. We saw this nice sunflower lemma and saw an application to D-heating set and D set packing. We will have a couple of more lectures on kernelization to follow in the due course. Okay. So, thanks for now.